Hi everyone, my name is Esin Pektas and I'm with the Aerospace Engineering program. Today I will be presenting Group 17 case study on the 1986 Space Shuttle Challenger disaster. This topic is especially interesting because of its connection to the aerospace industry and the important lessons it offers regarding engineering judgment, risk management, and safety culture. The Challenger disaster remains one of the most significant engineering ethics case studies because it involved both a technical failure and a breakdown in the decision-making process. Nearly 40 years later, engineers still study this event to better understand how communication, organizational pressure, and risk assessment can affect critical engineering decisions. In this presentation, we will discuss what happened, why it happened, and the lessons that continue to influence engineering practice today. For starters, this diagram shows the three major components of the space shuttle system: the orbiter, which carried the crew and payload, the external tank, which stored the liquid fuel, and the two solid rocket boosters, which helped lift the shuttle off the ground. Understanding these components is important because the failure that led to the Challenger disaster originated in one of the solid rocket boosters. On January 28, 1986, Space Shuttle Challenger lifted off from Kennedy Space Center and broke apart 73 seconds later, killing all 7 crew members on board. The immediate cause was the failure of O-ring seals in the right solid rocket booster during unusually cold weather conditions. However, the tragedy was not caused by a technical failure alone. Engineers at Morton Thiokol, the contractor responsible for the solid rocket boosters, warned that the cold temperatures created an unacceptable risk and recommended delaying the mission. During discussions with NASA, concerns about schedule impacts and mission delays contributed to significant pressures to proceed. Ultimately, management reversed the engineers' recommendation and the mission moved forward. As a result, Challenger became one of the most important engineering ethics case studies in history, highlighting the consequences of communication failures, organizational pressure, and poor decision making. We will discuss these ethical issues in more detail later in the presentation. Let's watch a brief video.
At 11:38 a.m. on January 28th, Challenger launched from Kennedy Space Center. Footage later showed that dark smoke began to jet from one of the right-side solid rocket booster's O-rings less than a second after liftoff began. The shuttle broke the sound barrier 40 seconds up, and at around 59 seconds, a plume of flame began to emit from the right-hand SRB. The crew wouldn't have known about this, as further evidenced by their yells of "woohoo" at 60 seconds, a mere quarter second before the flame began to contact the orbiter's massive external fuel tank. For spaceflight now, even if the crew had known what was happening, there was nothing they could have done. Just before 73 seconds came the last words from Challenger spoken by Mike Smith. Uh-oh. Immediately afterward, the shuttle was torn apart as the external fuel tank erupted into a massive fireball. A few seconds later, an object was seen descending slowly by parachute. Several TV stations began to focus on footage of the object and the shock and confusion that followed. However, it was only the nose cap of one of the SRBs.
The purpose of this case study is to understand both the technical and ethical factors that contributed to the Challenger disaster and identify lessons that engineers can apply today. The scope includes the engineering failure, the decision-making process leading up to the mission, and the professional responsibilities of engineers and managers when safety is at stake. One of the key technical challenges was O-ring blowby in the right solid rocket booster SRB. Because of the unusually cold temperatures, the O-rings did not fully seal the booster joint, allowing hot gases to escape. This blowby eroded seals and initiated the chain of events that ultimately led to the loss of Challenger. The case also highlights the challenges of making engineering decisions when operating outside previously tested conditions and with limited data available. These images show blowby from the right SRB shortly after ignition. The black smoke indicates that the cold O-rings failed to fully seal the joint, allowing hot gases to escape and begin the chain of events. Here is a video of the detail. at O-ring.
The Space Shuttle Challenger disaster could be traced to one mistake: the failure of these black rubber bands. They were meant to seal the right solid rocket booster joint. The O-rings, as they're called, were supposed to move into the groove to prevent the hot gases from leaking. But the cold weather caused both the primary and backup O-ring to stiffen, so they failed to stop the gas from escaping. As proof, scientist Richard Feynman dunked a rubber O-ring into a glass of ice water.
It doesn't stretch back, it stays the same dimension. I believe that has some significance for our problem.
This discovery put Feynman on the map. For the full video on his
The Challenger disaster is often studied as an engineering ethics case because the technical problem was known before the mission. The first ethical challenge was management overriding engineering concerns. Engineers at Morton Thiakol recommended against proceeding it because of the unusually cold temperatures, but that recommendation was later reversed. The second challenge was the conflict between public safety and schedule pressure. NASA was facing pressure to maintain its mission schedule, and safety concerns were not given the weight they deserved. Finally, there were communication and organizational failures. Critical technical information did not effectively reach all decision makers, and the concerns raised by engineers became diluted as they moved through the management chain. Together, these ethical failures contributed to a decision that ultimately had catastrophic consequences.
The rocket booster engineers understood that this element increased the risk of liftoff. These 5 engineers, who tried to stop the mission that day, detailed what happened and their concerns in a 1986 interview with NPR. "We all knew if the seals failed, the shuttle would blow up," said Roger Boisjonlay, one of the Challenger's engineers. The engineering team sounded the alarm the morning before the Challenger launch, calling their boss, who immediately organized a teleconference between NASA officials and the worried engineers. After considering their concerns, NASA leadership decided to press forward with the launch due to the fact that the mission had already been delayed 5 times before. This was a difficult position for the leadership team at NASA, but the decision should have been easy. It is exactly these kind of situations that you need experts on your team for. Instead of listening to sound advice from their people, they chose to put on their blinders and move forward with the launch. Lawrence Malloy, the project director of NASA's Marshall Space Flight Center, responded to the request of the engineers with, "When do you want me to launch? Next April?" NASA's decision not to listen to the advice of their experts led to devastating results.
This case highlights the importance of protecting engineering judgment when organizations face schedule, political, or management pressure. The Challenger disaster demonstrates the dangers of accepting known risks, or what we call normalization of deviance. It also reminds us that systems should be proven safe before proceeding, not the other way around. Ultimately, engineers have an ethical responsibility to place public safety above all other considerations. Our proposed solution focuses on treating the Challenger decision as a proper engineering decision, or PED, rather than a management decision. Because human lives were at risk, engineering judgment should have carried the greatest weight. The engineers recommended against proceeding below 53 degrees Fahrenheit because the O-rings were operating outside their proven qualification limits. Our approach also emphasizes informed consent and critical loyalty, meaning engineers should support the mission while still speaking up when safety concerns exist. This solution aligns with the NSPE Code of Ethics, which requires engineers to place public safety first and to act when their professional judgment is overruled. Finally, we reject the normalization of deviance and the reversal of the burden of proof. Instead of asking engineers to prove the system would fail, decision makers should have required evidence that it was safe to proceed. The main benefit of our solution is creating a culture where safety information is shared openly rather than being isolated within individual groups. When engineers, managers, and astronauts have access to the same information, concerns can be identified earlier and challenged before they become major risks. This approach helps reduce groupthink, strengthens informed decision-making, and allows engineers to raise concerns without fear of being ignored. Ultimately, it improves safety, increases transparency, and helps NASA maintain public trust while reducing the likelihood of similar failures in the future. We evaluated several alternative approaches to the Challenger decision. The actual decision was to proceed as scheduled, which resulted in the loss of 7 lives and the destruction of the vehicle. Other alternatives included implementing stricter procedures, redesigning the O-ring system, or creating an independent safety review committee. While each option offers some benefits, our preferred approach focuses on improving both the technical review process and the organizational culture so that safety concerns are communicated effectively and given appropriate weight in future decisions. In the end, Challenger was not just a failure of hardware. It was a failure to listen to the engineers who saw the warning signs. The lesson is simple. When human lives are at stake, safety must come before schedules, budgets, and organizational pressure. As engineers, our responsibility goes beyond calculations and designs. Sometimes the most important thing we do is have the courage to speak up. Challenger reminds us that engineering is not just about building things right. It's about doing the right thing. Thank you.